We treated the Hubble Ultra Deep Field like a limit. James Webb Space Telescope says the count may reach 2 trillion across the observable universe. Redshift reveals a busier cosmos than astrophysics expected. The dark space around us only seems empty because our eyes stop at the limits of our own light. Everything we've ever seen in the cosmos, stars, nebulae, clusters, distant galaxies, isn't the whole universe. It's just the layer whose light has managed to reach us. We're not seeing a border of space. We're seeing the age of light itself. Right now, as you listen to this, a photon from the most distant known galaxy is still traveling toward us, crossing millions upon millions of miles. It left its source when the universe was about 280 million years old. Long before the Sun, long before Earth, long before the Milky Way became a spiral. We're looking not into distance, but into deep time. For decades, it's seemed that this ancient layer contained around 200 billion galaxies. That was the number derived from the Hubble Space Telescope, which stared into a tiny patch of sky, stacked the light for days, and revealed thousands of worlds, even in a spot no bigger than a grain of sand held at arm's length. But then came the infrared vision of the James Webb Space Telescope, and everything changed. We hadn't missed a few percent. We had missed nearly a factor of 10. There weren't 200 billion galaxies. There were roughly 2 trillion. For every one we could see before, 9 more were hidden, too faint, too red-shifted, their light stretched by the expansion of space, until only infrared eyes could catch it. Imagine standing by a half-open door and judging the size of an entire house by a single lit hallway. The house could have many floors, corridors, or even extend beneath the ground. That's exactly what happens with the universe. We describe reality based on what light has revealed, not on what actually exists beyond. The most striking example is the Hubble Ultra Deep Field. The telescope gazed into what looked like nothing, a void so small you could cover it with the tip of a pin, and there in that microscopic patch of sky, it found about 10,000 galaxies, 10,000 star cities, each holding billions of suns in one infinitesimal corner of the heavens, scaled to the entire sky. That density gives us not a tidy round number, but a staggering one. At least 2 trillion galaxies within the region of space, whose light has had time to reach us over the last 13.8 billion years. And that leads to a simple but uncomfortable truth. We don't see the edge of the universe. We see only the edge of information. Wherever light is still on its way, we see darkness and mistake it for emptiness. But darkness in this case isn't absence, it's delay. The cosmos never promised to show us everything at once. There's another trap. When we say 2 trillion galaxies in the observable universe, it sounds final, as if someone has explored, counted, and signed off on the total. But it's only an estimate. Within our light bubble, the bubble expands because time moves forward, meaning that even this number isn't the end of the story. We already underestimated by a factor of 10 once. There's no reason to think it won't happen again. And that's what makes this discovery so powerful. We live inside a transparent sphere, defined by the speed of light and the age of the cosmos. We mistake that sphere for the whole of existence. We build models based on what we can see. But the visible is not the whole. For the first time, we have instruments precise enough to show that behind the old number was a far denser, earlier, more crowded cosmos. One more truth is worth saying out loud. When we look far away, we see young galaxies, but that doesn't mean they are still young now. In the present moment of cosmic time, most have already merged, evolved, and changed shape. We only see their childhood, because childhood light is what has reached us. We live in a museum of delayed images. Everything beyond is still sending its photographs. And even within this incomplete archive, we count roughly 2 trillion galaxies. So the most honest thing we can say about the universe is this. It's far denser than it seems, far wider than it looks, and far younger at the edge than it is at the center of our gaze. Everything else depends on how much more light we manage to collect. If it were just a pretty number, 200 billion or 2 trillion, we could smile and move on. But the number of galaxies is not decorative statistics. It is an input variable for the whole picture of the universe. It tells us how much ordinary matter there is, how early the first stellar cities began to assemble, how many sources of ionizing radiation there were to make the young universe transparent, and most importantly, how rare we really are. When we believe the entire observable region held about 200 billion galaxies, that already sounded overwhelming. In a universe like that, mind, life, special conditions, all of that could be filed under very unlikely but possible. But when it turns out there are about 10 times more galaxies, everything we called rare becomes rare only by our standards. The universe is not just large, it is massively repetitive. There is another layer. The lower galaxy count made our models behave nicely. Every cluster, every group, every dark halo had its slot. The moment we add 9 hidden galaxies for every visible one, we are saying, in the early eras of the cosmos, stars were forming faster than we built into our equations. That means more ordinary matter was already assembled. That means dark matter and dark energy had to spread that density farther than we thought. A mistake in the galaxy count is not a typo in a catalog. It is a warning that we tuned the universe to incomplete data. And there is the human part of the stake. With 200 billion galaxies, it was easy to keep a cozy image. The Milky Way is a major player. We have a clear address. We do not get lost on the cosmic map the moment we are surrounded, not by hundreds of billions, but by trillions of star islands. Our address turns into something like one spiral galaxy, somewhere on the outskirts of one group, at the edge of one supercluster, inside one strand of the cosmic web. Which means we are not the center. We are not even the exception. We are one of those that are visible only because their light has arrived. That is why the stakes are high. Either we accept a denser universe with early, fast, surprisingly mature galaxies, and then we have to rebuild the story of the cosmos, or we keep the comfortable version with 200 billion. And then we are knowingly holding on to a model that has already missed by an order of magnitude once. Before we can say, the universe is about 10 times richer, we have to be honest about where the old confidence came from. It was not pulled out of the air. It was a clean, careful, very disciplined picture, supported by a whole generation of telescopes and a whole generation of astronomers. At the end of the 20th century, the space telescope we now call the Edwin Hubble Space Telescope did something that at the time, many people thought was almost pointless. It was pointed not at a nebula, not at a planet, not at a bright cluster. It was pointed at almost nothing, at a blank patch of sky. An amateur telescope would have shown, as there is nothing here. And it was told, stay there. Watch. A day. Another day. A week. Shoot again. Stack the frames. Pull every last photon out of the dark. The result went into history as the deep field. It was like pulling the curtain back a crack and suddenly seeing not one street, but an entire city outside. In that tiny field of view, the telescope found thousands and thousands of tiny smudges. Most of them were not stars. They were whole galaxies, self-contained miniature universes, each with billions of suns and its own clouds and nebulae. The distances to them were enormous. Their light had been traveling for billions of years, but they were there, and that experiment proved the main thing. Even where the eye in an ordinary telescope see emptiness, the cosmos is packed with structure. After that, a very simple, very honest logic kicked in. If in this much sky we can see this many galaxies, then in the whole sky, which has a surface area millions of times larger, we will see proportionally more. That was a careful extrapolation, not fantasy, but statistics. That is how the estimate of about 200 billion galaxies was born for the region of space, whose light can reach us over the age of the universe. And the age, in plain words, is about 13.8 billion years. That number was instantly liked by cosmologists. First, it was humanly huge. 200 billion is not infinity, but it is already almost unimaginable. Second, it fit nicely into the models of the time. With roughly that density of star islands, you could explain large-scale structure, trace the growth of clusters, and tie it back to the observed cosmic microwave background, that ancient radiation that filled space about 380,000 years after the Big Bang. Everything lined up. There was another, very down-to-earth reason. That number matched what the instruments could actually do. Hubble was seeing what it was able to see, its wavelength range, its sensitivity, its exposure times. All of that created the feeling, we have reached the bottom, that beyond this is only noise, that there is nothing more to collect, and if there is nothing more to collect, then 200 billion becomes, that's all there is. That is how the canon appeared. Popular science books started repeating the same phrase. There are about 200 billion galaxies in the observable universe. Documentary films repeated it as a fact. Journalists loved the comparison. There are more stars than grains of sand on all the beaches of Earth. It became almost folklore. Schools repeated it. College courses repeated it. Around it, a picture formed where our Milky Way is a noticeable player. Not the giant of giants, but definitely not a speck in an ocean. The important thing to understand is this. That version was honest for its time. It did not come from a desire to shrink the universe. It came from the limits of the technology. We saw that much, so we counted that much. We looked in visible light, so we drew conclusions from visible light. We worked with an instrument of a certain depth, so we decided that depth was enough. There was, however, something in that first version that later came back to bite us. It was tied very tightly to what visible light can show, but light from the very earliest epochs has been stretched by the expansion of space. Its maximum brightness has slid into the infrared. We simply did not see those tiny, very distant, very young worlds that shine not white or blue, but deep red, already in the thermal part of the spectrum. For older telescopes, it was like trying to look at a faraway shore through fogged glass. So that first version is really a portrait of the universe seen by one telescope in one era. It is an honest photograph, but taken on a camera with low light sensitivity. As soon as we brought a better camera to the very same sky, structures began to appear that had not been there before. That elegant number had an ugly secret. It depended completely on what a single instrument was able to see. The Edwin Hubble Space Telescope was extraordinary for its time, but it was still just an eye with a sensitivity limit. If an object shines fainter than your threshold, it does not exist for you, not because it is not there, but because your optics say I cannot see it. First problem, range. Hubble worked mainly in visible and in near-infrared light. But while the light from the oldest galaxies was traveling toward us, the expanding fabric of space stretched its waves. What had once been blue and bright arrived as faint and red. And if it becomes redder than your instrument can confidently pick up, you do not put it on the list. Which means the farthest and the earliest candidates were being pushed into invisibility automatically. Second problem, depth and time. Even the famous Ultra Deep Field was built from hundreds and hundreds of stacked exposures. That meant to pull tens of thousands of distant galaxies out of the dark. The telescope had to stare at one point for many days. We cannot stare at the entire sky like that. We looked at a few microscopic patches and extrapolated them to the whole celestial sphere. That is normal for astronomy, but it always leaves a risk. What if the patch we chose was richer than average, or poorer than average? Third problem, the brightness floor. There is always a simple line. Everything brighter than this. I count everything fainter than this. I treat as noise. For faraway galaxies, that is dangerous. If you have a lot of very small, very faint, very distant objects, each one on its own might not cross the line. But if you could add them all together, you would get a meaningful amount of light. Those are exactly the crumbs of the universe Hubble was losing most often. Fourth problem, dark zones. Even on the deepest images, there are areas where you can tell something is there, but the instrument cannot resolve the shape. It could be tiny dwarf galaxies. It could be the first attempts at forming stellar systems. It could be small clusters half hidden by dust. For statistics, it is easier to call that background irregularity. than to figure out what is really inside. Fifth problem, human. Once a number lives in textbooks and popular books for 10, 15, 20 years, habit grows around it. Habit hides the assumptions. Everyone is used to saying about 200 billion. Everyone is used to pictures with a thick texture of galaxies. Everyone is used to the line. And maybe somewhere out there is life. And at that moment, it is very easy not to notice what exactly did we throw out at the photometry stage. Which tiny objects did we send to noise? Why are we so sure this one tiny patch of sky is representative of all sky? And finally, the sixth and most painful problem, dependence on a single window. Our we see 200 billion was, to a large extent, we see 200 billion with these eyes and in this band of light. The moment the infrared giant came online, sensitive to longer waves, everything that used to look empty started to fill with new dots. That is the sign of a crack. If your estimate collapses as soon as you look with a more sensitive eye, it was never a property of the universe. It was a property of the instrument. So the fair conclusion is simple, and it does not insult Hubble. It showed us how full the cosmos is, on the level it was able to show. But it also hid from us everything that was fainter, redder, and deeper in time. We built a whole story from the top, brightest layer, and the lower layers, the oldest, the most compact, the dimmest, stayed below the floor. That is exactly where the missing factor of 10 was sitting. What had once been blue and bright arrived as faint and red. And if it becomes redder than your instrument can confidently pick up, you do not put it on the list. Which means the farthest and the earliest candidates were being pushed into invisibility automatically. Second problem, depth and time. Even the famous Ultra Deep Field was built from hundreds and hundreds of stacked exposures. That meant to pull tens of thousands of distant galaxies out of the dark. The telescope had to stare at one point for many days. We cannot stare at the entire sky like that. We looked at a few microscopic patches and extrapolated them to the whole celestial sphere. That is normal for astronomy, but it always leaves a risk. What if the patch we chose was richer than average, or poorer than average? But if you could add them all together, you would get a meaningful amount of light. Those are exactly the crumbs of the universe Hubble was losing most often. Fourth problem, dark zones. Even on the deepest images, there are areas where you can tell something is there, but the instrument cannot resolve the shape. It could be tiny dwarf galaxies. It could be the first attempts at forming stellar systems. It could be small clusters half hidden by dust. For statistics, it is easier to call that background irregularity than to figure out what is really inside. Fifth problem, human. Once a number lives in textbooks and popular books for 10, 15, 20 years, habit grows around it. Habit hides the assumptions. Everyone is used to saying about 200 billion. Everyone is used to pictures with a thick texture of galaxies. Everyone is used to the line. And maybe, somewhere out there is life. And at that moment, it is very easy not to notice what exactly did we throw out at the photometry stage. Which tiny objects did we send to noise? Why are we so sure this one tiny patch of sky is representative of all sky? And finally, the sixth and most painful problem, dependence on a single window. Our we see 200 billion was to a large extent. We see 200 billion with these eyes and in this band of light. The moment the infrared giant came online, sensitive to longer waves, everything that used to look empty started to fill with new dots. That is the sign of a crack. If your estimate collapses, as soon as you look with a more sensitive eye, it was never a property of the universe. It was a property of the instrument. When the first deep infrared frames showed way too many distant galaxies, astronomers did not say, okay, let's redo the whole universe. That is not how science moves. First you ask, did we make a mistake in the instrument, in the processing, in the model? That is healthy skepticism. The first check was noise. Any telescope, even the most expensive and the newest, has background. Detectors warm up. Electronics add tiny spikes. Cosmic rays hit the sensor. If an object is very faint and very red, you can mistake a pretty noise blotch for a galaxy. So part of the community said, let's slow down and make sure the telescope did not just paint something that is not really there. The second check was gravitational lensing. A very massive object, like a galaxy cluster, bends space around it and acts like a magnifying glass. Light from far, faint galaxies passing by that glass is stretched and brightened. If your field of view includes many such lenses, you can get the false impression that there are too many distant galaxies in that direction. So one perfectly reasonable explanation was, maybe we are looking through an amplified patch of sky and treating it as typical. The third line was systematics, small but repeating errors in how we turn light into distance and age. To say, this is a very young, very far away galaxy, you have to measure how far its light has been shifted toward the red, and from that calculate how much space has expanded. If that chain has a built-in bias, several dozen objects can slide into earlier and farther than they really are. Supporters of this view said, let's recalibrate. Let's compare with ground-based observatories. Let's not declare a revolution after the first batch of images. There were even more cautious voices. They reminded everyone, we have already once extrapolated one tiny window of the sky to the entire sky and got a beautiful number. Maybe we are doing the same mistake again, just in the infrared. Maybe the James Webb Space Telescope happened to look into a patch where, for purely cosmic reasons, the density of early galaxies is above average. That can happen. The universe is not uniform, it has filaments, knots, and voids. So the skeptic was within his rights to say, we cannot be sure it is this crowded everywhere. And there was a deeper argument. If we accept that there were 10 times more galaxies already in the very early epoch, we have to shift the whole star formation timeline. Admit that stars and big structures started assembling almost immediately after the universe became transparent. That is a big blow to the comfortable story of a slowly maturing cosmos. So before we move such a big piece of the story, let us check again. Maybe the data are the issue. All of these objections mattered because the new picture was hitting several areas at once. The mass of ordinary matter, the growth path of galaxies, the makeup of the young universe, and the need to explain excess light in the infrared. When one observation forces you to tweak 4 parts of theory at the same time, the reaction, let's double check, is the only sane reaction. But this skepticism had a limit. If it were only noise, the signal would drop out after cleaning. If it were only lensing, the dense spots would always sit behind massive foreground clusters. If it were only systematics, different teams with different pipelines would get different numbers. But they started getting the same ones, and that was the uncomfortable part for the fans of the old number. The anomaly was repeatable, which means the explanation the instrument made it up no longer works. This is how science really behaves. First, it tries to throw away the surprising result, and only when it cannot, it starts to believe it. The skeptical explanations were reasonable, but they ran into the usual problem good skepticism runs into. Once you test them one by one, they start to deflate. First, independence. Data on very distant, very red galaxies were processed by different research groups. Not one team with its favorite pipeline, but several teams in different institutes on different software. If this had been a quirk of one reduction method, the results would have split. They did not. Different people saw the same thing. At very early times, the universe looks more crowded with galaxies than in the old picture. Second, calibration. When a new space observatory starts working, its spectra and brightness measurements are compared to what ground-based telescopes and earlier missions have already measured. If the James Webb Space Telescope were systematically making objects look brighter, it would have shown up immediately. The same targets would suddenly become brighter than the archive. That did not happen. So the brightness scale is basically right, which means the faint galaxies are real faint galaxies, not noise dressed up as galaxies. Third, repeatability. Some of the suspicious sky fields were observed again. If this had been a one-off spike or a bad frame, the galaxies would have vanished on the second pass. They did not. They stayed where they were. Their light was still shifted far into the red. Their brightness still said very far and very early. In science, that is called a stable signal. Fourth, the redshift itself. We do not estimate distance to the farthest galaxies by eye. We do it by how far their light is pushed to longer wavelengths. That push is created by the expansion of space itself. If we were getting the redshift wrong, the errors would scatter. Some galaxies would come out closer, some farther. Instead, we see a whole group whose light is strongly redshifted in the same direction. That does not look like random error. That looks like a real distant population. And fifth, if the main explanation were, this is all gravitational lenses, then the weirdest, farthest, brightest for their age galaxies would all sit behind big foreground clusters that magnified them. But some of them are found in fields where there is no such cosmic magnifying glass. In other words, they are bright enough to be seen even without lensing. And that is a direct hit against the idea you just got lucky with the line of sight. Put together, it leaves a simple conclusion. The story the instrument made it up does not hold here. And if it does not hold, we are left with the simplest and hardest explanation. In the early universe, there really were more visible galaxies than we expected, which means the old count for the observable volume was low. Sometimes you do not need a brand new telescope, you just need one decisive frame. In the story about how many galaxies there really are, that frame was the Hubble Ultra Deep Field. The telescope stared for a very long time at a patch of sky that to a normal eye is pure black. No constellation, no nebula, no Milky Way, just a dark spot. And then that spot lit up like a hidden vault of the cosmos in a tiny piece of sky small enough to cover with the tip of a pin at arm's length. There turned out to be about 10,000 galaxies, not stars, not single bright dots, actual galaxies, spirals, ellipticals, small irregular ones, stretched ones, young ones, red ones, very distant ones. That was the click moment. They show you a place where nothing was supposed to be and say, look, space is packed here too. You cannot argue with that. You can see it. Here the geometry is everything. We are not talking about a wide belt of sky or a 10-degree sector. We are talking about a speck, a tiny circle. If that one circle gives you 10,000 worlds, then the whole sky, the entire celestial dome around us, with that same density gives you not hundreds of billions, but trillions. That is exactly how the estimate of about 2 trillion galaxies inside the region whose light has reached us over the age of the universe was born. What the infrared telescope did later was simply to confirm this was not a lucky spot. It is a property of the deep universe. As soon as you look a little farther into the red, there where it used to be dark water, new points begin to show through. It is like lowering a flashlight 1 meter deeper and suddenly seeing, under the layer of big stones, another layer of small, very dense gravel. Hubble showed us the top layer. Infrared observations showed the bottom one. The ultra-deep field became evidence for 2 reasons. First, it was taken blind. Nobody pre-selected a fat, rich area of the sky. They took an empty spot, and it turned out to be full. Second, it was good enough that you could do statistics on it, not just gasp at a pretty picture. You could measure brightnesses, shapes, approximate distances. It was not just visual shock. It was measurable material you could scale. And once you take that measurable material and spread it over the whole sky, you get exactly that too much. Too much for the old version. Too much to keep the number at 200 billion. Too much to keep saying it is probably just noise. Let's not rush. The evidence was too visible. There is a third reason this is treated as the key piece. This observation perfectly explains why the older instruments missed it. They were really only seeing the brightest, largest members of that same layer. Everything smaller and dimmer just never rose above the background. Once we had the ability to look longer and to catch longer wavelengths, the small early galaxies started popping out. They had been there all along. We did not add them. We finally saw them. And at that point, it is honest to say out loud, if a sand-grain patch of sky holds 10,000 galaxies, then we cannot keep picturing the cosmos as sparse, empty, and cold. It looks more like a suspension, a thick cosmic sawdust, a huge, very spread out, but still fairly uniform medium. And then the phrase 2 trillion galaxies in the observable universe stops sounding bold. It starts sounding cautious, because we are still counting only what has had time to send us its light. When you have a beautiful piece of evidence, a tiny field with 10,000 galaxies in it, the next honest step is always the same. Test whether it survives someone else's math and someone else's telescope. In other words, if I count this a different way, do I get the same answer? First thing astronomers did was run the objects through photometric models. These are calculations that, from the brightness and the color of the light, tell you how many stars are in a galaxy, how old or young they are, and how much dust and gas there is. If the galaxies had been too bright for their age, the models would have flagged it. But the models said something else. Yes, they are young. Yes, they are far. Yes, they are compact. But their light is perfectly consistent with what a real stellar population can produce. So the fairy tale version, it is just a noise flare, did not fly. Second, they checked the spectrum. The light that reaches us can be broken apart by wavelength. And you can see which elements are present, what temperature the source has, and whether there are odd gaps. If the problem were in the instrument, the spectrum would have shown it, crooked lines, wrong positions. Instead, the spectra showed a clean shift to the red. Exactly what you expect from objects that are very far away and very early in time, which means cosmic expansion really did stretch their light. And that is exactly what we are seeing. Third step, measure the redshift in more than one way. There is the fast photometric way, from the overall color judge, how red it is, and estimate distance. And there is the slower, more exact spectroscopic way, from specific element lines compute the shift. If we had been wrong about the distances, those two methods would have disagreed. But for a whole set of objects they agreed. That is a very strong hint that we are truly looking into cosmic childhood, not into some processing artifact. Fourth, they compared it with mass distribution maps that come from a completely different channel, from how big structures bend space. If there are really lots of galaxies in some direction, that should also show up in the way they curve space-time, and that started to match too. So the storyline there is nothing there. The telescope just painted it in. Does not hold. Independent measurements say there is matter in those directions. Fifth, they brought in other observatories. If an unusual result shows up not only on one space instrument, but also in ground-based data, old archives and repeat observations, then the phrase "maybe it is just a glitch" has nowhere to live. In our case, it had nowhere to live. Yes, different telescopes go to different depths, but the overall picture, many young, many distant, many faint, stayed. In the end, the control test gave exactly the answer many people quietly did not want. It would have been convenient if the ultra deep field were just a statistical outlier. It would have been convenient if the infrared telescope had simply overestimated brightness. It would have been convenient if gravitational lensing had blown everything up and fooled us. But no, different methods, different models, different instruments, all point in the same direction. The early universe was denser and more active than the old 200 billion version allowed. Now we can say it outright. We did not see the universe become bigger. We saw that it had been this big all along. We just were not looking deep enough. Our first counts described not the real cosmos, but the part of its light our instruments at the time could collect. What the deep fields and the infrared surveys are showing is basically the universe's baby album. We are looking at it when it was roughly from 400 million to about 1 billion years old. That is an incredibly early era. At that point, galaxies are small, hyperactive, often messy in shape, with a furious rate of star formation. There are many of them precisely because, back then, matter was being assembled faster than we were used to assuming. If in that early slice we already counted about 2 trillion galaxies, it tells us only one thing. Our old number of 200 billion was a photograph of the top floor, not of the whole building. How sure are we? Since the same picture came out for different teams, on different datasets, in different bands, we can stop talking in maybe terms and start talking in very likely terms. A paper would say confidence level close to 95%. In film language, it's simpler. Almost certainly the young universe was denser and richer in galaxies than we thought. It is important not to mix things up. We have not proved that the entire universe contains exactly 2 trillion galaxies. We have shown that inside the region, we can see there are at least that many. And that region, our light bubble, is just everything whose light has had 13.8 billion years to reach us. Everything beyond that light horizon, everything whose photons are still on the way, is not in the count and cannot be, which means the full universe, the one we will never see whole, may be even richer. So we end up with a simple, slightly sobering formula. We live inside a bubble of observable cosmos. We have counted pretty well what this bubble has already shown us. We know, with high confidence, it is not hundreds of billions of galaxies. It is at least trillions. And we just as honestly admit, beyond this bubble, there is light that has not arrived yet, and galaxies we cannot list yet. That is a healthy place for modern cosmology. For once, we are not pretending to know everything. We are saying, this layer, the one we can see, we understand. Beyond it is where light has not yet caught up, and that is exactly where the next telescopes will look. We have already proved that the sky that looked empty is actually crowded. The logical next step is to look even deeper and across a wider area. Right now, we have a telescope that can see the universe as it was about 280 million years after it was born. The next missions are being built to do 2 things: to catch even fainter galaxies, and to shoot deep fields not just in a few lucky places, but across the sky. First line, the big future observatories like LUVOIR. That is a large, powerful, very precise space telescope with a mirror bigger than what we have now. It will be able to give us high resolution and high sensitivity at the same time. For us, that means something very simple. The fuzzy red blotch we see today will show up tomorrow as a fully resolved young galaxy with internal structure. And the argument, is this noise or is this real, will just disappear. Second line, the missions that used to fly under wide field, now under the name Roman. Their job is not to drill to record depth in one point, but to make a very deep, already wide map of the sky. That matters because our main doubts came exactly from extrapolating one tiny window to the whole sky. If Roman shows the same density of early galaxies right away over a big sector, then the talk about trillions stops being a guess and becomes straight statistics. Third line, concepts like the Origin Space Telescope. These are missions tuned to the far infrared. That is where the oldest, dust-caked, most muted galaxies are hiding. The ones that are barely visible, even to James Webb today. If we start catching those as well, the number of star islands inside our observable bubble will go up again. And there is a human motive too. All of these machines are being designed with the new picture in mind. We do not live in an empty universe. We live in a universe that was already busy in the first few 100 million years. So we need to look exactly for those worlds. Very early, very compact, very fast. We are no longer building telescopes only for beautiful spirals and nebulae, like in the 20th century. We are building them to see what the cosmos looked like the moment it first became transparent. So what comes next here does not mean someday later we might check. It means we already have the technology to tighten the number. We already know where to look, and we already know that the empty patches are not actually empty. We used to think the darkness between the stars was just emptiness. Now we know, even in the darkest point of the sky, there can be 10,000 galaxies, which means the cosmos has not been silent for billions of years. It has been speaking very softly, and we had to learn how to listen. Every beam of light that reaches us is not just light. It is a memory of the moment when that galaxy was only switching on, when it did not yet have mature spirals around it, when space was still expanding more slowly, when the universe was young. We receive those memories now, in a completely different era, and we stitch them together into our picture of reality. And still, it is only a picture inside our bubble. Beyond that wall of light, photons are still on their way that we will never see. Not because we built the wrong telescopes, but because the universe has not had time to deliver its whole archive to us. We live in a cosmos that has not finished its story. There is a strange kind of comfort in that. We did not get an empty universe. We got an overfilled one. Not a cold one, but one that has been working since the beginning. We know about millions and millions of star cities, only because a few instruments once looked into nothing and refused to believe it was nothing. That means we, too, should not trust apparent emptiness at first glance. What we are seeing today is an early photo, black and white, grainy, taken on a very long exposure. But even from that frame, it is clear. The universe was rich from the very first shot.